Thank you to Stuart and Rob for the invitation. It's a great honour to be here today. We've heard a lot about the fantastic achievements at Manchester over the past 65 years. And I think Stuart and Rob would like me to look ahead to see what's coming. Because there's no reason why Manchester can't have another, even better 65 years going forward. So just for those of you that don't know who I am, I'm here actually today with several hats on. So my day job is at the National Physical Laboratory, NPL, in southwest London, where I lead the electrochemistry group. We have a 100-year history of working in corrosion, not that I'm trying to top anyone, when I arrived in 2002 to NPL, we only did corrosion in the electrochemistry group. Since then, we have broadened out into low-carbon energy, including hydrogen, fuel cells, electrolyzers, carbon capture, nuclear, in much the same way that Manchester has been doing over the same period of time. But I've also got very involved in external organisations because corrosion is a very difficult topic to enthuse people about. It's really easy to sell the concept of research on electric vehicles, hydrogen, bioengineering, all those kind of things. People throw money at you. Corrosion is a bit more difficult, and it's a smaller community of people who recognise just how important this is and how important it's going to be in the future. So one of my other problems is I have clearly difficulty saying no to things, which I suspect Rob and Stuart knew when they asked me to speak today. So at the moment, I'm president of the World Corrosion Organization, which is a UN-affiliated body trying to raise awareness amongst the general public and funding bodies and policymakers about just how important corrosion is to the future. And we've linked this very strongly to the UN Sustainable Development Goals, as I'll say in a minute. I'm also the incoming Vice President of the European Federation of Corrosion and, as Stephen mentioned, a past President of ICOR. I'm going to say a few words about the WCO. I mean, it's a very small organisation and not many people know about it. And one of the things that we need to do is make it more prominent. And we're going to be doing that through a rebranding and dedicated social media presence, working with the EFC and ICOR and other organisations like Manchester. But we've recently refocused our objectives to make it really clear that we're not interested in hosting technical events, we're not interested in making money through training or accreditation, we just want people to know about corrosion. So we've sharpened our objectives at last September's board meeting. I won't read them out, but they're written there. And it's linking it much more strongly to the UN Sustainable Development Goals so that we can actually raise awareness properly. And we do have a Corrosion Awareness Day. It's coming up on April 24. I know that Manchester students always get involved, so very keen to hear about what you're going to do this year. But we also have a new award, which is not a technical award like the awards that Stuart showed earlier. It's an awareness award, so it could go to anyone who does anything to raise the importance of corrosion in the general public. But I'm here today to talk about low-carbon technologies, and that's really part of the WCO vision, because a lot of the work that has been done in corrosion over the last 100 years has been strongly linked to fossil fuels. And rightly so, it's the backbone of our economy, it's how we live and survive. We need to transition, as you've heard, but there are a load of opportunities out there. And I'm going to give one specific example of how learnings developed with fossil fuel corrosion science and engineering can very rapidly make a big difference in a new field where those ideas are completely unknown. I thought I would mention, and this came up when Stuart mentioned China. At last year's Corrosion Awareness Day, my good friend Enhu Han from Shenyang and Guangzhou gave a presentation, and we were all talking about how great it was that we had 30 people at a webinar or 200 people attending an event. He gave a talk on Corrosion Awareness Day to 200,000 people. So, what they're doing over there absolutely dwarfs us in terms of numbers. And I had made a video for that event, which I just fired over to him. Had no idea it was going to go to that many people. It was actually beamed out to every school that was taking part, and that was why the numbers were so high. I've also noticed I'm wearing the same shirt as I am today, so I need a new wardrobe. One of the other things we've done within the WCO is start to publish position papers on low carbon. So last year we published this paper in Materials and Corrosion, which I encourage you to look at. It's basically saying everything that I'm saying today, but there's a lot more detail in there about the different areas where corrosion is important in these new emerging technologies. So please do have a look at it if you can. But I'm just going to give you an example of some work recently that we've done at NPL. That, you know, it's very simple concepts in corrosion science, but applied to water electrolysis, where these concepts are completely alien. And getting this paper published was a massive struggle. We had to go through about 6 sets of reviewers, all of whom were saying, no, this is rubbish, this is not science, I don't believe it. We finally got it published, but when I speak to corrosion scientists about it, they go, yeah, that's obvious. Like, why wasn't this published years ago? And the topic is hydrogen refueling stations, where we're generating hydrogen from water and renewable electricity, ideally, to generate green hydrogen. And this is an example of the refueling station on our Teddington site in southwest London, where it is the busiest electrolyzer-powered hydrogen refueling station. It was developed for cars, probably about 10 years ago now it was designed. It's probably going to be mothballed in the next year or two because the UK policy and indeed world policy has recognised that hydrogen is really only suitable for heavy-duty transport. And unfortunately in Bushy Park, where we are, they're not going to let HGVs come in and out. It would also need to be redesigned. So it's going to be quietly retired, but the learnings that we've got from it have been very useful to understand how to develop this kind of infrastructure and roll it out. This is how an electrolyzer works. So this is a very special material. It's a proton-conducting membrane that's electron insulating. And when you supply water to the anode and apply a potential of about 2 volts between the anode and cathode, you oxidize water to form oxygen. Protons then migrate through the membrane to the cathode, where they react with the electrons to form hydrogen. And you can collect and store this hydrogen in a big tank at 1,000 bar of pressure and dispense it to vehicles. So this is, you know, a reasonably new technology. It's been developed in the UK by ITM Power, who manufacture the refueling station that's on our Teddington site, and many others throughout the world. And they're one of the top 3 companies in the world manufacturing this type of water electrolyzer, which is a proton exchange membrane, or PEM water electrolyzer. This is a bit of more detail about the structure, and we're very interested today in these 2 components, the bipolar plate and the porous transport layer. So all of the fancy electrochemistry happens at the electrodes, the anode catalyst layer, and the cathode catalyst layer. So this is a very expensive material. This is iridium or ruthenium oxide, and the cathode is platinum-based, supported on carbon. But we're interested in these less sexy components because actually they make up a greater share of the volume, mass, and cost of the stack. And just to, I guess, give you a framework for the work, you apply a voltage across this cell, and with respect to the hydrogen electrode, the potential of the anode electrode is about 2 volts during operation, and the cathode is about 0 volts because it's generating hydrogen, so it actually acts like a hydrogen reference electrode. And the common assumption all across industry and throughout academia is that all of these materials on the bipolar plate and the porous transport layer sit at this potential of 2 volts during operation. And for those corrosion scientists, and particularly cathodic protection scientists and engineers in the room, you will know pretty much straight away that because this porous transport layer contains deionized water, that actually this 2 volts does not transfer across to the bipolar plate. It's analogous to throwing power in CP, that the bipolar plate will actually sit at its open circuit potential and will be effectively unaware that it's close to an electrode at 2 volts. And so when we came to look at this system, we were actually studying the membrane and the anode catalyst layer and looking at corrosion mechanisms there. And I just said to myself, well, why do people assume that this is at 2 volts? It can't be. So we set out to measure that. The short story, Stuart, if you want to stop here, was that I was right and everyone else was wrong. But if we have time, I'll just go through some of the work. So this is a stack. This is what the device looks like. They come in various shapes and sizes, but you can stack them up in hundreds of cells to generate enough hydrogen to power a refueling station. And just to reiterate about the cost, the porous transport layer and the bipolar plates together make up about 40% of the cost of a stack. So if you can make them from cheaper materials, you can dramatically reduce the cost of green hydrogen. So, what do they use? At the moment, they use platinum-coated titanium, which is incredibly expensive, both to source and to manufacture. And our question was, can we actually use something a lot cheaper, particularly for the bipolar plate? So this was the neat little system that we had developed probably 10 years ago to look at fuel cells for the exact same reason. And again, when we did this work on fuel cells, we showed this decoupling phenomenon, and we published it because really it only made a difference to the testing. If I went back 10 years and I wanted to make a lot of money, I probably wouldn't have published that fuel cell work, because little did I know that when you apply it to water electrolyzers, it is very commercially significant. So that's a commercial reality lesson. Think very hard before you publish anything that you do. Although I don't regret it, because the information needs to get out there. So this is a reference electrode externally, where we connect it via a solid salt bridge to any point within the cell where we want to measure the local potential. So we're measuring the corrosion potential of a component within the cell. This time we're looking at the bipolar plate, which in a single cell we just call a current collector. And I guess the neat trick about this salt bridge is that it's a Nafion tube. So it's made of the same material as the membrane, that is proton conducting. So it's a solid proton conducting salt bridge with an external reference electrode. And that is just a really neat way of making a small hole. This is a 1 millimeter diameter tube, and you can terminate it anywhere and measure the local corrosion potential. So that's what we did. And again, just like we predicted, rather than seeing the full 2 volts as you would at the anode electrode, we found that the current collector was completely decoupled from the cell potential. So there was a large potential drop through that deionized water layer in the porous transport layer. That led us to ask, what about the porous transport layer? Because yes, we can replace all of the bipolar plates with something like carbon-coated stainless steel, which would be much cheaper. Can we also replace the porous transport layer? So I'm not going to go through the full details of the model, but essentially we came up with this decoupling coefficient, that basically the higher the solution resistance, the more decoupling there is, but it also depends on the electrochemical properties of the porous transport layer material, which in this case is platinum. So that's the equation for the decoupling coefficient. We then also developed a 1D electrochemical model of the anode potential profile, so from the full 2 volts at the electrode down to the 1 volt open circuit potential of the platinum in oxygen. I won't go through the details, but this is just to show that there is a real model behind these curves that I'm going to show you. You can read the paper in your own time. So this is the model, and these are the 2 plots that are most relevant to service. So you have deionized water, type 1 water and type 2 water in red, and you can see that there is a sharp potential drop over the length scale of a couple of hundred microns. So actually most of the porous transport layer and all of the bipolar plate is sitting at its open circuit potential, rather than at the high potential of the electrode that you would predict if you read any other papers or talked to anyone who worked for an electrolyzer manufacturer. As you increase the conductivity of the water, then you do see that potential transmitted all the way to the bipolar plate. But in a real operating electrolyzer where you have an ion exchange resin, the conductivity of the water is kept very low. So these are just very unrealistic conditions to demonstrate the throwing power analogy. We also experimentally validated the model using 4 different depths of reference electrode measurement in the porous transport layer, again using these external hydrogen reference electrodes. And the measurements did show that we could confirm this potential drop over the distance of a few hundred microns into the porous transport layer. So again, the first time anyone has shown this either theoretically or experimentally. And it's a very simple idea. Anyone who came to this with any kind of knowledge of corrosion would have had this same idea. But it's just bringing those two communities together. Looking at ex situ measurements, just to confirm what the situation is, you have the platinum-coated titanium sitting at just above 1 volt in oxygen. You have the carbon-coated stainless steel and the 316L sitting at about 0.5 volts relative to the hydrogen electrode. And then when you galvanically couple them together ex situ, it tends to sit closer to the potential of the platinum because it's more electrochemically active. I'm going to skip in some of the detail here in the interest of time because I know we are running a little bit late, but most of these measurements just confirm that the bipolar plate is sitting at this decoupled potential. So we set up a cell for 7 days with a carbon-coated 316L current collector, and we showed that it sat at a completely different potential from the anode. We also ran a longer 30-day test, this time with no reference electrode, just to kind of take a look at the carbon-coated stainless steel at the end of the test, and it showed that there was no corrosion or evidence of degradation, whereas anyone who had ever set up a test before but put the carbon in contact with the electrode, it just disappears in seconds. So you have to have some kind of spacer layer there to make sure that doesn't happen. And again, looking at the polarization curves before and after confirmed that there was very little degradation during the test. So this is our idea. This is what the situation is at the moment. You have the catalyst layer, and everything to the left of it is platinum-coated titanium. The porous transport layer, the mesh, and the bipolar plate. Our idea is we can replace all of these materials with carbon-coated stainless steel as long as we have a thin, couple of hundred, maybe 300 micron thick microporous layer that could be platinum-coated titanium or other corrosion-resistant material, just to provide a buffer through which the potential drops in this corrosive zone. And this could really drop the cost of these stacks if this idea could be rolled out. So this summarizes graphically the high potential at the catalyst layer, the open circuit potential of the bipolar plate. It's not sitting at this potential, as everyone assumed prior to the work, and even we had to argue with world-leading electrolyzer scientists just to get this published. And the key thing is that through the porous transport layer, the potential drops like this because of the low conductivity of the deionized water in the pores. So I encourage you to have a look at the paper if you have time. It was published last year. I would like to also just acknowledge my collaborators from NPL and our colleagues at Sandvik Materials, who are very interested in this because they make carbon-coated stainless steel. And my final slide is just to look ahead. So I've just given you one example of a simple concept from corrosion science that is applied in a new field of green hydrogen production. There are lots of other examples like that of work that's going on here at Manchester and in other places around the world. These opportunities are massive, and I mean, looking on the Manchester website yesterday at what you're doing in the nuclear area, in batteries, in wind, in hydrogen, particularly looking at hydrogen aircraft, that's a big opportunity, and in carbon capture. All these areas are going to be crying out for corrosion scientists and engineers, and if we don't keep training them at places like Manchester, we're threatening the future on the planet. So I encourage you all to raise awareness of corrosion, advocate for places like Manchester and the education here so that it can continue, because we are going to need these people going forward, and it's vital to the future of the planet. So thank you very much.
Do you have any questions for Gareth? Hey guys, I'll kick off.
Sure.
Where do you think the biggest challenges are? You've mentioned these various areas. Where do you think the biggest contributions that corrosion engineers can make?
So yeah, I think for me, the biggest challenges aren't technical. They're actually political and cultural. So I think it's selling the importance of corrosion. And you know, from talking to Stuart over the years, I know how hard he's fought to keep corrosion front and centre of people's minds. And we need more people like that to do that. And I'm hoping that I can be one of those going forward. But we need everyone to step forward and recognise that we can do all the great science and engineering that we want, but if we're not selling the concept of this, the importance of this topic to the global community, to politicians, to decision makers, then our future is just going to narrow. And I think people will realise it's important, but it'll be too late. And we don't want a gap to develop, particularly in skills. We need young people to be educated in corrosion, we need qualifications, we need training, we need to adapt to the new forms of energy that are coming. So I think that's the challenge. I could list a lot of technical challenges, but they will be solved. It's getting the people and the structures and the funding together that is the most important thing.
Any other questions?
Gareth, we talked about this before, but you know, through the World Corrosion Organisation, how can we influence politicians? I mean, through ICOR, we know things are, bridges aren't getting painted, infrastructure's not getting painted. We've got the corrosion engineers, we've got the technology. How do we influence decision makers to put money into these areas?
Yeah. It's difficult. And you know, the World Corrosion Organisation has been going for nearly 20 years. And I think it's tried to do too much. It's spread itself very thin, and it's a very small organisation. It's, you know, it's about 10 people without much resource. I think the key is to write position papers and documents that capture the information that then can be used at local level by ICOR, by AMP, by the Australasian Corrosion Association, where they know the local issues. But it's generating that material and linking it strongly to the UN Sustainable Development Goals. That's going to be a key strategy. But it's not going to be easy.
Any other questions? Let's thank Gareth again.